Section 1. Introduction to Statistical Learning Theories. Statistical learning theories form the backbone of machine learning. They provide a framework to understand how algorithms learn patterns from data. At the core, statistical learning theories explore the relationship between the generalization error and the complexity of the model. These theories help in designing models that can perform well, not just on training data, but also on unseen data. One of the key concepts in statistical learning theory is the bias-variance trade-off. Bias refers to errors due to overly simplistic models, while variance refers to errors from overly complex models. Balancing these two is crucial for optimal model performance. Another fundamental aspect is the Vapnik-Chervonenkis, or VC dimension, which measures the capacity of a model to fit diverse data sets. The theory also delves into the consistency of learning algorithms, ensuring that as more data becomes available, the model's performance improves. This is crucial for developing reliable and scalable machine learning systems. Moreover, understanding the sample complexity, which determines the amount of data needed for a model to learn effectively, is vital for practical applications. In recent years, statistical learning theories have evolved to include complex neural network models. These theories provide insights into how deep learning models generalize and the factors influencing their performance. As we delve deeper into neural networks, these foundational theories will serve as a guiding light for understanding advanced concepts. Section 2. Universal approximation theorems and their implications. The universal approximation theorem is a cornerstone in neural network theory. It states that a feed-forward network with a single hidden layer can approximate any continuous function given sufficient neurons. This theorem underlines the potential of neural networks to model complex functions and solve a wide range of problems. The implications of this theorem are profound. It means that in theory, neural networks can learn any mapping from inputs to outputs, making them incredibly powerful tools for machine learning. However, practical applications require careful consideration of the network's architecture, training process, and computational resources. Despite the theoretical guarantee, achieving universal approximation in practice can be challenging. The number of neurons required may be impractically large, leading to issues like overfitting and computational inefficiency. Therefore, researchers and practitioners often use deeper networks with multiple layers to achieve the desired approximation with fewer neurons. The theorem also highlights the importance of activation functions. Non-linear activation functions, such as ReLU or sigmoid, are crucial for the network's ability to approximate complex functions. Without non-linearity, a neural network would merely be a linear model, significantly limiting its capabilities. Understanding the universal approximation theorem helps in appreciating the flexibility and power of neural networks. It sets the stage for exploring more advanced topics, such as the trade-offs between depth and width in network design. Section 3. Depth versus width trade-offs in neural network design. In neural network design, a fundamental question is whether to prioritize depth, the number of layers, or width, the number of neurons per layer. Both approaches have their advantages and trade-offs. Understanding these trade-offs is crucial for building efficient neural networks. Deeper networks can capture more complex patterns and hierarchical features. Each layer extracts higher-level abstractions from the input data, enabling the network to learn intricate relationships. However, Deeper networks are also more prone to issues like vanishing and exploding gradients, which can hinder training. On the other hand, wider networks with more neurons per layer can also approximate complex functions, as per the universal approximation theorem. Wider networks tend to require fewer layers, which can simplify the training process. However, they may be less efficient in capturing hierarchical features compared to deeper networks. The choice between depth and width often depends on the specific problem and computational resources. For instance, convolutional neural networks, or CNNs, used in image processing often benefit from deeper architectures, enabling them to learn spatial hierarchies. In contrast, some tasks may favor wider networks for their simplicity and ease of training. Researchers have proposed various techniques to mitigate the challenges associated with deep networks, such as batch normalization and residual connections. These techniques help stabilize training and improve the performance of deep networks. Balancing depth and width, therefore, requires a nuanced understanding of the problem at hand and the available tools. Section 4. Optimization landscapes and navigational techniques. Understanding the optimization landscape of neural networks is essential for effective training. The optimization landscape refers to the surface formed by the loss function over the parameter space. Navigating this landscape involves finding the optimal parameters that minimize the loss function. The optimization landscape of neural networks is highly non-convex, characterized by numerous local minima, saddle points, and flat regions. This complexity makes finding the global minimum challenging. Gradient-based optimization algorithms, such as stochastic gradient descent, or SGD, are commonly used to navigate this landscape. One of the key challenges is avoiding local minima and saddle points, which can trap the optimization process. Techniques like momentum, learning rate schedules, and adaptive learning rates, such as the ADAM optimizer, help in overcoming these obstacles. These methods adjust the optimization trajectory, enabling the model to escape local minima and converge to better solutions. Another important aspect is the role of initialization. Proper initialization of network weights can significantly impact the optimization process. Techniques like Xavier or He initialization help in setting the initial weights to appropriate values, facilitating effective training. Researchers have also explored advanced methods, such as second-order optimization algorithms, like Newton's method, and meta-optimization techniques. These methods aim to provide a more detailed understanding of the optimization landscape and improve the efficiency of training neural networks. Mastering these techniques is crucial for developing robust and efficient neural models. Section 5. Generalization theories and regularization techniques. Generalization refers to a model's ability to perform well on unseen data. Understanding generalization is crucial for developing models that are not just accurate on training data, but also on new, unseen data. Several theories and techniques help in achieving better generalization in neural networks. One of the foundational concepts is the Occam's razor principle, which suggests that simpler models tend to generalize better. In the context of neural networks, this translates into controlling the complexity of the model through techniques like regularization. Regularization methods, such as L1 and L2 regularization, add a penalty term to the loss function, discouraging overly complex models. Dropout is another effective regularization technique. By randomly dropping neurons during training, Dropout prevents the network from relying too heavily on specific neurons, promoting robustness and better generalization. This technique has been widely adopted in various neural network architectures. Data augmentation is also a powerful regularization method. By artificially increasing the diversity of the training data through transformations, like rotations and translations, data augmentation helps the model learn more generalized features. This technique is particularly effective in tasks like image classification. Other advanced techniques include ensemble methods, which combine predictions from multiple models to improve generalization. Ensemble methods, such as bagging and boosting, leverage the strengths of different models, reducing the risk of overfitting. Understanding and applying these generalization theories and techniques are essential for building robust neural networks. Section 6. Information bottleneck principle and Bayesian techniques. The information bottleneck principle is a theoretical framework that provides insights into how neural networks compress and retain relevant information. The principle suggests that a good model should compress the input data while preserving the information necessary for the task. This trade-off between compression and relevance is crucial for understanding neural network behavior. In practice, the information bottleneck principle can guide the design of network architectures and training processes. For instance, techniques like bottleneck layers in convolutional networks explicitly implement this principle, forcing the network to focus on essential features. This approach helps in building more efficient and interpretable models. Bayesian techniques offer another powerful framework for understanding and improving neural networks. By treating model parameters as random variables with probability distributions, Bayesian methods provide a principled way to quantify uncertainty. This is particularly useful in scenarios where uncertainty estimation is critical, such as medical diagnosis or autonomous driving. Bayesian neural networks, or BNNs, leverage techniques like variational inference and Markov chain Monte Carlo, or MCMC, to approximate the posterior distributions of the model parameters. These methods enable the network to capture the uncertainty in predictions, enhancing robustness and reliability. Combining the information bottleneck principle with Bayesian techniques provides a comprehensive theoretical framework for neural network design and training. These principles help in developing models that are not only accurate, but also interpretable and robust, addressing some of the key challenges in modern machine learning. Section 7. Neural networks as dynamical systems. Viewing neural networks as dynamical systems provides a deeper understanding of their behavior. In this perspective, the training process is seen as the evolution of the system's state under the influence of the optimization algorithm. This dynamical systems view offers valuable insights into the stability, convergence, and generalization properties of neural networks. One of the key concepts in this framework is the notion of attractors. Attractors are states or sets of states towards which the system tends to evolve. Understanding the attractors in the optimization landscape helps in analyzing the convergence behavior of neural networks. Stable attractors correspond to well-generalizing solutions, while unstable attractors may lead to poor generalization. Another important aspect is the Lyapunov stability theory, which provides tools for analyzing the stability of dynamical systems. Applying this theory to neural networks helps in understanding the conditions under which the optimization process converges to a stable solution. This analysis is crucial for designing robust training algorithms. The dynamical systems perspective also sheds light on phenomena like vanishing and exploding gradients. These issues can be understood as the system's trajectories diverging or converging too rapidly, leading to instability. Techniques like gradient clipping and normalization help in mitigating these issues, ensuring stable training. By treating neural networks as dynamical systems, researchers can leverage a rich set of mathematical tools to analyze and improve their behavior. This approach enhances our understanding of neural networks, paving the way for more robust and efficient models. Section 8. Theoretical insights into CNNs, RNNs, and attention mechanisms. Convolutional neural networks, or CNNs, are specifically designed for processing grid-like data, such as images. The theoretical foundation of CNNs lies in their ability to capture local patterns through convolutional layers. These layers apply filters to the input data, extracting features like edges and textures. The hierarchical structure of CNNs allows them to learn increasingly complex patterns at deeper layers. Recurrent neural networks, or RNNs, on the other hand, are designed for sequential data. The theoretical insight into RNNs revolves around their ability to maintain a hidden state that captures information from previous time steps. This allows RNNs to model temporal dependencies, making them suitable for tasks like language modeling and time series prediction. The emergence of attention mechanisms has further advanced the field of neural networks. Attention mechanisms allow models to focus on relevant parts of the input data, dynamically adjusting their focus based on the task. This has led to the development of models like transformers, which have revolutionized natural language processing by enabling efficient parallelization and improved performance. The key theoretical insight behind attention mechanisms is the concept of self-attention. Self-attention computes a weighted sum of input features, where the weights are determined by the relevance of each feature to the task. This allows the model to capture long-range dependencies and relationships, enhancing its ability to understand complex data. Understanding the theoretical foundations of CNNs, RNNs, and attention mechanisms is crucial for leveraging their strengths in various applications. These insights provide a roadmap for designing and training advanced neural network architectures. Section 9. Generative models, NTK frameworks, and symmetries. Generative models aim to model the distribution of data, enabling them to generate new, realistic samples. Theoretical insights into generative models revolve around their ability to capture the underlying structure of the data. Techniques like variational autoencoders, or VAEs, and generative adversarial networks, known as GANs, have demonstrated remarkable capabilities in generating high-quality samples. The Neural Tangent Kernel, or NTK framework, provides a theoretical perspective on the training dynamics of neural networks. The NTK approximates the behavior of deep networks during training, offering insights into their convergence and generalization properties. This framework helps in understanding why deep networks often perform well despite their complexity. Symmetries and invariances play a crucial role in the design of neural networks. by incorporating symmetries such as translation invariance in convolutional neural networks, or CNNs. Neural networks can leverage the inherent structure of the data. This not only improves performance, but also enhances the interpretability of the models. The role of symmetries extends beyond architecture design. Techniques like data augmentation often exploit symmetries to enhance the diversity of training data. Understanding the theoretical significance of symmetries and invariances helps in developing more robust and efficient neural networks. Generative models, NTK frameworks, and symmetries offer rich theoretical insights that drive the development of advanced neural network models. These concepts provide a deeper understanding of how neural networks learn and generalize, paving the way for innovative applications. Section 10. Advanced Optimization Methods and Adversarial Robustness. Advanced optimization methods are essential for training complex neural networks effectively. Techniques like second-order optimization algorithms, including Newton's method and quasi-Newton methods, leverage curvature information to improve convergence rates. These methods offer a more refined approach compared to first-order techniques like gradient descent. Another advanced optimization technique is meta-optimization, which involves optimizing the optimization algorithm itself. Meta-optimization techniques, such as learning rate schedules and adaptive learning rates, dynamically adjust the optimization process based on the training progress. These methods enhance the efficiency and stability of training neural networks. Adversarial robustness is a critical aspect of neural network security. Adversarial attacks involve perturbing input data in a way that causes the model to make incorrect predictions. Understanding the theoretical underpinnings of adversarial robustness helps in developing models that are resilient to such attacks. Techniques like adversarial training and defensive distillation enhance the robustness of neural networks. Adversarial training involves augmenting the training data with adversarial examples, helping the model learn to recognize and withstand attacks. Defensive distillation, on the other hand, trains the model to be less sensitive to small perturbations in the input data. Combining advanced optimization methods with techniques for adversarial robustness leads to the development of robust and efficient neural networks. These approaches address some of the key challenges in modern machine learning, ensuring reliable and secure models. Section 11. Continual Learning and Sparse Coding Theories. Continual learning, also known as lifelong learning, focuses on developing models that can learn and adapt over time. Unlike traditional models that are trained on a fixed dataset, continual learning models continuously update their knowledge with new data. This requires addressing challenges like catastrophic forgetting, where new learning overwrites previously acquired knowledge. Theoretical insights into continual learning involve techniques like regularization-based methods and memory-based approaches. Regularization-based methods, such as elastic weight consolidation, or EWC, add constraints to the optimization process to preserve important parameters from previous tasks. Memory-based approaches, on the other hand, store and replay past experiences to reinforce learning. Sparse coding is another important concept in neural networks, inspired by the brain's ability to represent information efficiently. Sparse coding theories suggest that neural networks should represent data using a small number of active neurons, promoting efficiency and reducing redundancy. This has led to the development of techniques like L1 regularization and sparse autoencoders. Sparse coding enhances the interpretability and efficiency of neural networks. By focusing on essential features, sparse coding helps in developing compact and robust models. Understanding the theoretical foundations of sparse coding provides valuable insights into the design of neural networks that mimic the brain's efficiency. Continual learning and sparse coding theories offer valuable perspectives for developing adaptive and efficient neural networks. These theories address key challenges in machine learning, paving the way for models that can learn and evolve over time. Section 12. Neural networks as differential equations and GNNs. Viewing neural networks through the lens of differential equations offers a powerful theoretical framework. In this perspective, the layers of a neural network are seen as discrete time steps in the evolution of a dynamical system. This analogy provides insights into the stability and convergence properties of neural networks. The neural ordinary differential equations, or neural ODE, framework formalizes this perspective. Neural ODEs model the continuous evolution of the hidden states using differential equations, providing a more flexible and interpretable approach to neural network design. This framework has been applied to various tasks, including time series analysis and generative modeling. Graph neural networks, or GNNs, extend the capabilities of traditional neural networks to graph-structured data. The theoretical foundation of GNNs lies in their ability to perform message passing, where information is exchanged between nodes in a graph. This enables GNNs to capture the relationships and dependencies in graph data, making them suitable for tasks like social network analysis and molecular modeling. Understanding the theoretical insights behind GNNs involves concepts like graph convolutions and spectral graph theory. Graph convolutions generalize the concept of convolution to graph-structured data, allowing GNNs to learn hierarchical features. Spectral graph theory provides tools for analyzing the properties of graphs and designing efficient GNN architectures. Viewing neural networks as differential equations and exploring the theoretical foundations of GNNs offer valuable perspectives for developing advanced models. These approaches enhance the flexibility and applicability of neural networks, enabling them to tackle a broader range of problems. Thank you for watching.